Very rarely will you be able to measure exact amounts of reactants for a chemical reaction. And many times a reaction will run more efficiently, kinetically or thermodynamically, if one of the reactants is in excess. So we have to address the very common case in chemistry where we put given amounts of reactants into the system, but there's an excess of some reactants and a single limiting reactant. Later in the lecture, we'll also quantify that invisible member of the reactions, the energy. It makes sense that the amount of energy absorbed or emitted in the reaction will also be dependent on the amounts of reactants. So let's get at it. A limiting reactant is a reactant that is completely consumed in a chemical process. Obviously, the amount of product we get in the reaction will be restricted by this limiting reactant. And if we convert all the limiting reactant to the product, the amount of product we obtained in the computation is called the theoretical yield. Now, since we live in the real world, and there are many ways we can lose products in our efforts to isolate them, we almost never expect to obtain the full theoretical yield of product. The amount of product we can expect to obtain in a reaction is called the actual yield. I know, not the most original of names. Now, when making new compounds, it's very common to report the percent yield for the reaction. It implies to others how difficult the reaction may be to run or how much starting material they need to purchase if they want to make a given amount of the material product. The percent yield is obtained by simply computing the ratio of the actual yield divided by the theoretical yield times 100. Now, to demonstrate the concepts of limiting reactant, theoretical yield, and percent yield, let's use our old friend the ammonia reaction. Let's say we have 27.0 grams of nitrogen gas and 6.7 grams of hydrogen gas. The question we first ask is, what is the limiting reactant? To find the limiting reactant, we take each reactant separately and calculate the amount of product each would produce using the methods in the previous lecture on stoichiometry. Now, we only need to compute the moles of product at first. The computation that produces the smallest number of moles of product wins. That will be our limiting reactant, and the amount of product we calculate from this will be our theoretical yield. Now, the amount of ammonia we can make with 27 grams of nitrogen gas is 1.93 moles of ammonia. The amount of ammonia gas we can make with 6.7 grams of hydrogen gas is 2.2 moles of ammonia. The winner is nitrogen gas. Nitrogen gas is our limiting reactant. And remember, the computation also gives us the theoretical yield for this reaction. So from these computations, we expect 1.93 moles of ammonia will be the maximum amount of ammonia we can hope to obtain in this reaction, given the limited amount of nitrogen gas. Now, let's run the reaction using the reactant amounts, 27 grams of nitrogen gas and 6.7 grams of hydrogen gas. Let's say after running the reaction in our lab and then isolating the ammonia product as best as we can, we obtained only 29 grams of ammonia. What is the percent yield? Well, right now, we know that the theoretical yield is 1.93 moles of ammonia. We will convert this theoretical yield in moles to grams of ammonia using the molar mass. 1.93 moles of NH3 is equivalent to 32.9 grams of ammonia if we multiply 1.93 moles by the molecular mass of ammonia. To get the percent yield, we divide the 29.0 grams actual yield by the 32.9 grams theoretical yield and multiply 100 by 100 to get things into percentages, obtaining a percent yield of 88.2%. There is one other reactant or product that we haven't dealt with yet, and that is the energy that would be absorbed in an endothermic reaction or emitted in an exothermic reaction. And just as we would deal with computing amounts of reactant and product compounds, we can compute energy too. So let's look at the balanced combustion reaction of methanol liquid. The enthalpy of this reaction is minus 1,451.4 kilojoules per mole of the reaction as written. We learned previously that the enthalpy at constant pressure is equivalent to the amount of heat energy absorbed or emitted in the reaction. There are a variety of ways that we find this energy value experimentally using straightforward thermochemistry, but that'll have to be material for a future lecture series in chemistry and thermodynamics. For now, we're just going to accept the idea that we know this molar energy value. Now, we know this is an exothermic reaction because of the negative sign on the enthalpy. Thus, we get the following molar relationships. For every 2 moles of methanol that combusts, for every 3 moles of oxygen we use, for every 2 moles of CO2 produced, for every 4 moles of liquid water made in the reaction, we can expect to get 1,451.4 kilojoules of heat emitted in an exothermic process. And if we double the reaction, multiplying all the stoichiometric coefficients by 2, we would also have to multiply the energy by 2. Okay, with this added chemical data in our equation, we can answer questions like, how much energy would be produced by the complete combustion of 100 grams of methanol? As always, we get to moles of methanol as soon as we can, and then use our chemical equation and the mole relationships it provides to get to the energy. So first, we get to the moles of methanol by the molecular mass, and then we know that for every 2 moles of methanol that combusts, minus 1,451.4 kilojoules of energy is produced, giving us minus 2,264 kilojoules of energy produced by the combustion of 100 grams of methanol. Now, we preserve the sign on the energy so that everyone knows that this was energy emitted in an exothermic process. There we have it, stoichiometry. Congratulations. If you've been following along with this introductory series of lectures, we have finished our story, and the roof of our chemistry house is complete. Well, for now. It was a privilege to have you join me on this trip as we looked at the fundamental concepts that govern this science called chemistry. But be very aware that we have just started this journey. The hole has no bottom, and we are just beginning to awake and see the chemical world. There is a lifetime of discovery in chemistry that awaits you, and I look forward to maybe seeing you again. Be well, my friends. Catch you later.